Welcome to week 3 of pre-calculus. Our first topic this week is transformations of functions. We will look at a number of types of transformations of functions. One of them is vertical shifts. Think about this question. If you have the graph of function f, what happens when you add to f a constant? If you think about it, you will see that what happens with the graph is that you shift vertically by that constant. More precisely, if the constant is positive, like in this example, the constant is positive 1, you shift the graph by 1 unit upward. And if the constant is negative, you shift the graph by 1 unit downward. That is a vertical shift. Given a function f, a new function f plus constant k is a vertical shift of f. We always shift by absolute value of k units, and the sign of k determines the direction in which we shift. If k is positive, we shift upward. If k is negative, we shift downward. If, for example, I wanted to draw the graph of the function f minus 1, it would look like this. F of x minus 1. This is the easiest type of transformations, vertical shifts. Now, let's look at horizontal shifts. What happens if you add or subtract to the argument of the function, not to the function itself? Note that here we add k to the function, whereas here h is subtracted inside the parentheses, meaning that h is subtracted from the argument of the function. Such a transformation is called a horizontal shift, and we will see in a minute that it is indeed graphically a horizontal shift. More precisely, if h is a positive number, we shift the graph of f to the right by h. And if h is a negative number, like in this example, here h is negative 1. We shift by the value of negative h to the left. Let us explain why. Well, suppose we have the graph of f and say f takes value b at the point A. Suppose now we also have the graph of g, which is f at x plus 1. The question is, at what point will g take value b? Well, I claim g will take value b at the point a minus 1. That is because g at a minus 1 is, by the definition of g, f at a minus 1 plus 1. And of course, that's f at a, which is b. So we clearly see that G is kind of lagging behind F by 1 unit, meaning that whenever F at some point A takes value B, G will take that same value B at point A minus 1. If you think of X as time, you can say that G is 1 unit of time behind F. F takes value B at time A, G takes value B at time A minus 1. All right. And of course, the same stays for any other H, not necessarily -1. In general, if we have the graph of F, and F takes value B at point A, and we have the graph of G, which is some F at X minus H, we can ask the same question. At what point will G take value B? Let us try G of A plus H, perhaps. Because when you compute G of A plus H, you will get F at X. X in this case is A plus H, and then negative H from the definition of G. And that is, of course, F at A, and that is B. Now, we see from here that when H is positive, we should move the graph of F to the left. And when H is negative, we should move the graph of F to the right. Why is that again? Suppose H is positive. F takes value B at point A, G will take value B at point A plus H, so arguments should be by H units smaller to produce the same value. That corresponds to moving to the left. For example, if H is 2, and say F at 3 is 7, G now is F at X minus 2. At what point will G take value 7? We can see that G will take value 7 at 5. That is because G at 5, by the definition of G, is F at 5 minus 2, which is F at 3, which is 7. So subtracting positive H from the argument of F corresponds to shifting the graph to the right. And subtracting a negative H from the argument of F, or which is the same, adding a positive H to the argument of F, makes G lag behind F. If we consider the function h here, or rather perhaps j of x being f of x plus 2. And you ask the same question about j. At what point will j take value 7? I claim j will take value 7 at point perhaps 1, or we will see whether it's 1 or not. J at 1 is, all right, let's think again. At what point will j take value 7? Let's call it maybe a first. J at a is f at a plus 2, and in this to result in 7, a at a plus 2 has to be equal to 3, because that's where f takes value 7. So we must have a plus 2 to be 3, in which case a must be 1, and I was originally correct. J at 1 is f at 1 plus 2, which is f at 3, which is 7. Now compare G and J. G is leading ahead of f by 2 units, and J is lagging behind f by 2 units. G was obtained by subtracting 2 units from the argument of f, and we move the graph of f to the right, and J was obtained by subtracting 2 units from the argument of f, so we move the graph of f one more time. J was obtained by adding to the argument of f 2 units, or subtracting negative 2 units. So we move the graph of f by 2 units to the left to produce the graph of J. All right. That was horizontal shifts. We will have more examples involving horizontal shifts. So don't worry if you don't immediately understand what's going on. You will learn from examples. The very first example we look at is graphing f at x minus 2 plus 4 when f is the absolute value of x. Well, let me show this to you step by step. Let's draw the absolute value of x first. Now, let us forget about adding 4 for a second. Let us pretend this 4 is not here. Can we construct the graph of f at x minus 2? We can. As we just learned, the graph of f at x minus 2 is obtained from the graph of f by a horizontal shift of 2 units. So I should simply shift the graph of f which is absolute value of x, to the right, by 2 units. That will produce a different graph, which will look like this. So the angle of absolute value of x was at 0, 0, shifting to the right, we get the special point at 2, 0. The graph of f at x minus 2, which is absolute value of x minus 2. Now finally, let's unforget the plus 4 and construct the graph of h. How is the graph of h different from the graph of f at x minus 2? It's different by adding this plus 4, and adding the plus 4 corresponds to a vertical shift by 4 units upward. So let me move this text here a little bit further up. So to construct the graph of h now, I take the graph of f at x minus 2, which is absolute value of x minus 2, and shift it by 4 units upward. Shift f at x minus 2, which is absolute value of x minus 2, by 4 units upward. That will be the graph of h, which will look the following way. The special point now will be not at 2, 0. It will be at 2, 4 once we shift upward by 4. By the way, this y-intercept is of course 0, 2. When we shift by 4 units upward, the special point will be at 2, 4. And we again get this V-shaped graph. This time, this is the graph of h. Which is f at x minus 2 plus 4, which is absolute value of x minus 2 plus 4. And this finishes the graph. This finishes the example. One important comment that I would like to make here about this problem is the following. In this particular example, the order of transformations didn't matter. We first shifted to the right, and then we shifted upward. We could just as well shift upward by 4 units, and then shift by 2 units to the right, obtaining the same graph. It is, however, not the case in many other problems. We will have examples where the order of transformations, the order in which transformations are performed, is very much important because different orders result in different pictures. So let's write this down. In this problem, unlike many others, unlike many other problems, the order of transformations, or rather the order in which the transformations were performed, did not matter. However, again, this won't be the case in many other problems, so you have to be very careful thinking about which transformations you do first. We will talk about this later, and we will see examples where this is important. All right, let us now move on to the next example. Here the problem is to reconstruct the formula from the transformation of the square root function. Presumably, someone took the square root function, applied some transformations, and the resultant picture is what you see. So how can we reconstruct the formula for this graph? Well, let us first of all draw the new coordinate axis. And indeed, we see that this is the graph of root x. It passes through the point 1, 1. That's because root of 1 is 1. It passes through the point 4, 2. Or at least it should. And we can easily see what happened with the coordinate axis. The origin moved 1 unit to the right, horizontally, 1 unit to the right, and 2 units upward. So we can immediately recognize that this is the graph of square root of x. Now, to move it 1 unit to the right, we need to subtract 1 from x. And then to move it 2 units upward, we have to add 2. Okay. In the next example, we need to write a formula for a transformation of the reciprocal function 1 over x that shifts the function's graph 1 unit to the right and 1 unit up. Again, in this problem, just like in the square root example, it will not matter in which order you perform the transformations. So let us draw the reciprocal function. So for the reciprocal function, the axes actually play an important role in the sense that the vertical axis is a vertical asymptote and the horizontal axis is a horizontal asymptote. We'll talk about asymptotes later. For now, let's just say these are the lines that the graph approaches as close as you wish, but never touches them. So here is the graph of 1 over x. Let's apply the moving to the right transformation. When we move this 1 unit to the right, this will also move the vertical asymptote 1 unit to the right. So let me draw a new set of coordinate axes. The new vertical asymptote will be at 1. And the new graph will look the following way. The horizontal asymptote stays. A shift by 1 unit to the right will result in this graph being that of 1 over x minus 1. And accordingly, the point 0, comma negative 1 is the y-intercept. Now finally, let us apply the other transformation, which is shifting this graph 1 unit upward. Shift upward by 1 unit. This time, the horizontal asymptote shifts. So a new set of coordinate axes. Vertical asymptote at 1. And horizontal asymptote at 1. And the graph now looks the following way. By the way, what is the formula for the new graph? The formula for the new graph is 1 over x minus 1 plus 1. And now the graph passes through the origin. Okay, now the conversation switches to horizontal and vertical reflections, another type of graph transformations. So let's first speak about vertical reflection. See, we have the graph of f. What happens when you place a minus in front of f? As is easy to understand, what happens is the graph of f reflects about the x-axis to produce the graph of negative f of x. Let's see why. Let's say this point on the graph of f is a comma b. I claim that the point with coordinates a comma negative b will be on the graph of negative f of x. Naturally, the 2 points are symmetric about the x-axis. Simply because they have the same first coordinate, they lie on a vertical line. Moreover, being on this vertical line, they are equidistant. They're equally distant from the x-axis. Well, the fact that the point a comma b is on the graph of f is logically equivalent to b being f at a. But b being f at a is logically equivalent to negative b being negative f at a. And negative b being negative f at a is logically equivalent to the point a comma negative b on the graph of negative f. So once again, placing a minus in front of a function simply reflects the graph of your function about the x-axis. Now let's talk about a horizontal reflection. Horizontal reflections occur when you introduce a minus in front of the variable. More precisely, when you replace x by negative x inside the function. That will result in your graph reflecting symmetrically about the vertical axis. Let us see why. Let us take that point again, a comma b. I claim that upon reflection of this graph about the vertical axis, this point will be a comma, negative a comma b. Let's see why. A comma b is on graph of f if and only if b is f at a. But b is f at a if and only if b is f at negative a. Now, what does that mean? B equals f at negative a. It means that the point negative a comma b is on the graph of f at negative x. If you were to replace x here by negative a, you would have gotten f at negative a. All right. Now, why is this point negative a comma b a horizontal reflection of the point a comma b? Well, that is because they share the second coordinate, b, implying that the 2 points lie on a horizontal line, y equals b. And also their first coordinates have the same absolute value. Absolute value of a equals absolute value of negative a. implying the 2 points are at the same distance from the vertical axis. Hence, the 2 points are symmetrical about the vertical axis. This distance is A and this distance is A, much like this distance is B and this distance is B. Let us practice transformations with examples. In this example, for instance, we need to reflect both vertically and horizontally the graphs of these two functions, root x and absolute value of x minus 1. Let me draw a coordinate axis. Let's start with the graph of square root of x. We know it looks like this. Now, what happens when we reflect this graph vertically? Naturally, we get the graph of negative root x. How about a horizontal reflection? Reflecting horizontally, we will get the graph of square root of negative x. Now, what about the other example? Absolute value of x minus 1. Let me perhaps create a new page. Because I'm running out of space here. So this time, for part B of this example, we work with the graph of g, which is absolute value of x minus 1. How does that graph look like? Well, we can recognize that this is the graph of absolute value of x. Simply shift it to the right by 1 unit. To the right because we subtract 1. If this is 1, we will get a graph like this. Now, if we were to reflect this graph vertically, what would we get? We would have gotten the graph that looks very much similar to this one. Let me use red. All we need to do is just to put a minus in front of the absolute value. Now, how about a horizontal a horizontal reflection? To obtain a horizontal reflection, we need to replace x by negative x. So instead of absolute value of x minus 1, we actually get absolute value of negative x minus 1. I can factor out negative sign now. It will be negative x plus 1. And because the absolute value of a product is the product of absolute values, that's absolute value of negative 1 times absolute value of x plus 1. Of course, absolute value of negative 1 is 1. So that is simply absolute value of x plus 1. And we again can recognize that this is simply x minus negative 1, which is the graph of absolute value of x shifted by 1 unit to the left this time. The h here is negative. Whenever h is negative in a horizontal shift, we shift to the left. Okay, that finishes that example. Let me get back onto the previous page and do the next example. We have here function f given by a table, and we need to produce the tables for other functions. Negative f at negative argument, f at x plus 3, and f at x minus 2. First of all, let us understand that negative f at x will be vertical reflection. F at negative x will be a horizontal reflection. In part C, we have function j. That we realize is a horizontal shift by 3 units to the left. And in part D, we have a vertical shift by 2 units downward. Okay, let us construct the tables. First of all, let us know the important fact here. The domain of the functions g and the function I is the same as that of f. That is because G and I don't involve any changes in the argument. The domains of H and J will be different. So let us start with constructing tables for the functions G and I. Function G simply puts a minus in front of each value of f. So I should take values from the row corresponding to f and negate them. -1, -3, -7, and -11. Now for the function I simply subtract 2 from each value of f. One minus 2 is -1, 3 minus 2 is 1, 7 minus 2 is 5, and 11 minus 2 is 9. Okay, let us now create the table for the function h. Note that the domain of h will be different. Exactly how different? The domain of h will be symmetric to the domain of f with respect to 0. In other words, I should take all the input values for f and negate them. The function role will stay the same. The values of the function don't change. It's only where those values are taken, which is what's changing. So instead of 2, 4, 6, and 8, I should write here their negatives. -2, -4, -6, and -8. For example, let's check that h at -4 is really 3. Well, h at -4 is by definition of h, f at -4. But that is f at 4, and by definition of f at 4 is 3. Let us now construct the table for the function j. The domain of the function j also will be different from the domain of function f. More precisely, the domain of the function j will be the domain of the function f shifted to the left by 3 units. So the function role again will not change. One, 3, 7, 11. Rather, it's where those 4 values are taken is what's different. I should now take every value in the domain of f and subtract 3 out of it. So that'll give me -1, 1, 3, and 5. We can check why, for instance, j at 3 is 7. J at 3 is by definition of j, f at 3 plus 3. which is f at 6, but f at 6 is indeed 7. This finishes this example. On the next page, the conversation switches to a very important concept: even functions and odd functions. Let us first define them. A function is called even if for every x in the domain of that function, f at x equals f at negative x. Remember that f at negative x has its graph symmetric about the vertical axis to the graph of f. And the two functions being equal immediately implies that a function is even if and only if its graph stays the same upon a horizontal reflection, or, which is the same said in a different way, a function is even if and only if its graph is symmetric about the vertical axis. The example that you know is y equals x squared. Indeed, negative x, which is f at negative x, squared equals x squared, which is f at x. And as you see, the graph is symmetric about the vertical axis. A function is called odd if placing a minus sign in front of the argument corresponds to placing a minus sign in front of the function. Which you can also write that f equals negative f at negative x. Again, recall that f at negative x corresponds to a horizontal reflection, and placing a minus in front of the function corresponds to a vertical reflection. So the definition of an odd function simply says that a function is odd if and only if its graph stays the same after two transformations. When you perform first a horizontal transformation and then a horizontal reflection and then a vertical reflection. Here is one example. Consider the cubic parabola f at x equals x cubed. When you replace x by negative x, you perform a horizontal reflection. And of course, a horizontal reflection here is not the same as the original function. But when you put a minus in front of f at negative x to produce negative f at negative x, you now perform a vertical reflection. And as you see, after these two transformations, first horizontal reflection, then vertical, or we could do vertical reflection first, then horizontal, we do end up with the same graph as the original one. Algebraically, that simply means that negative of the cube of negative x is, as you can immediately see, the same as x cubed, which is f at x. We will later see that the function f equals x to any odd power has the same property. X raised to any odd power will be a function that is odd. One important comment here to make is that in both definitions, for even functions and odd functions, we necessarily assume that the domain of our function is symmetric about 0. What does that mean? It means that if x belongs to the domain, then negative x also belongs to the domain. So if the domain is, if these are the x's in the domain, we must have an interval like that to the left of 0. Symmetry about 0. Note also that not every function is either odd or even. There are functions that are neither odd nor even. For example, take the same cubic parabola and shift it upward by 1 unit. You can immediately see that it's not even because the graph is not symmetric about the vertical axis, and it's not odd either because two transformations, vertical and horizontal, do not produce the same graph. One thing I forgot to mention, and it's really important, is that when you perform first a horizontal reflection of any graph, horizontal reflection, then vertical, that corresponds to reflection about the origin. Let me add a page and perhaps explain this a little further. We have a point a comma b on the graph of some function and perform a horizontal reflection. We will end up with point negative a comma b. But now say we perform a vertical reflection after that. That will result in a point negative a comma negative b. Now compare the points a comma b and negative a comma negative b. Clearly they lie on the point they are reflections about the origin of each other. Why is that? A comma b and negative a negative b are reflections about the origin of each other. What does that mean? Well, it means exactly that. Well, first, it means that they lie on the same line. We can easily check that. They lie on the same line, although perhaps we won't do this here. The line passing through the origin and through the point AB, we can actually do this here. What is the line that passes through the origin and the point A comma B? Well, using the point slope form, we can write this line as y minus 0 equals slope b minus 0 over a minus 0 times x minus 0, which means y equals b over a times x. That is the equation of the line that passes through the origin and the point AB. Now, what happens if I plug instead of x the point negative a? Y at negative a will be b over a times negative a, and that's negative b. Correct? This computation implies that the 3 points a comma b, 0, 0, and negative a comma negative b lie on the same line, are concurrent. Excuse me, collinear. Concurrent is something different. These 3 points are collinear. They lie on the same line. Second, I claim that they are equidistant from the origin, right? The distance from either point a comma b or negative a comma negative b to the origin is, if you use Pythagorean theorem or the formula for the distance between 2 points, this distance being a and this distance being b. So the hypotenuse in this right triangle is simply square root of a squared plus b squared. Now, these two facts combined together, that the 2 points belong to the same, that the 3 points belong to the same line, and a comma b and negative a comma negative b being equidistant from the origin, imply that a comma b and negative a comma negative b are symmetric about the origin. So again, the graph of an odd function is symmetric about the origin, which in the example of the cubic parabola we can see immediately. But enough theory here. Let us see some examples. In this example, for each of the given functions, we need to determine whether they are even, odd, or neither. Say for the function a, f is x cubed plus 2x. I claim this function is odd. Let's check that f at negative x is negative f at x. F at negative x is negative x cubed plus 2 times negative x. Negative x cubed is negative x cubed, and here we get negative 2x, and factoring out the minus, we get x cubed plus 2x. Which is of course negative f of x. Hence, f is odd. You can try to check if f is odd or even, if f is even, and you will see that f is not even. For function in example b, x to the fourth plus 3x squared plus 7, I claim that it's neither. Let's see what g at negative x is. It's negative x to the fourth power. Actually, I am incorrect. Let's compute it. 3 negative x squared plus 7, because all powers are even. Raising negative x is the same as raising x. We get x to the fourth plus 3x squared plus 7, which is g at x. And so g is even. Finally, for example C, we see immediately that g is even because h is even. H at negative x is the root of absolute value of negative x. And of course, negative sign doesn't matter here. Absolute value is the same. And so h is even. By the way, what does the graph of h look like? Well, when x is positive, you simply get the graph of root x. And when h is negative, you get root of negative x. And as we know, placing a negative in front of x reflects the graph. So we will have the other branch look like this. Altogether, this is the graph of the function square root of absolute value of x. All right, let us perhaps make a pause here, and we will continue and talk about other transformations a little bit later. Thank you.